James Webb has spotted a tiny puzzling smudge of light that may be the oldest galaxy ever seen, shining from the very dawn of the universe. Today we explore why this object is so strange, and what it could mean for our picture of the early galaxies. If you enjoy discoveries like this, please like, subscribe and share. In the first moments after the Big Bang, the universe is hot, dense and simple. Space itself expands rapidly, carrying matter and radiation with it. There are no stars or galaxies, no separate clouds or clusters. Instead, there is a nearly uniform mixture of particles and light spread through all of space. Temperatures are so high that ordinary atoms cannot exist. Protons, neutrons and electrons move quickly, colliding with each other and with photons, which are particles of light. In this early state, matter and radiation are tightly coupled. Photons scatter off charged particles again and again, changing direction so often that light cannot travel freely for long distances. The universe behaves like a smooth fireball, in which every region shines and interacts with every other nearby region through constant collisions. As time passes, expansion continues. When space stretches, the distance between particles grows and the overall density falls. With lower density, the average collision rate decreases, and with each step in time, the temperature drops. The energy of the photons decreases as their wavelengths stretch with the expansion. What began as extremely energetic radiation gradually shifts toward less energetic forms. The fireball does not stop glowing, but its glow softens and cools. During the first small fractions of a second, the fundamental forces of nature take on the forms they have today. The balance between matter and radiation changes as particles and antiparticles appear and annihilate, leaving behind a small excess of matter. This leftover matter, mostly in the form of protons and neutrons, becomes the raw material for all later structures. Even in this simple phase, tiny irregularities exist. Quantum fluctuations from the very early universe leave small differences in density from place to place, slightly increasing the amount of matter here and slightly decreasing it there. These variations are extremely small compared with the overall smoothness, but they are present. As the universe expands and cools, they remain as gentle imprints on the otherwise uniform fireball. Within the first few minutes, conditions change enough for light nuclei to form. Protons and neutrons combine in nuclear reactions to create deuterium, helium, and small amounts of other light elements. This phase, known as primordial nucleosynthesis, sets the initial mix of nuclei in the universe. The temperature is still far too high for electrons to join these nuclei to make neutral atoms, but the basic building blocks are in place. Most of the mass resides in hydrogen and helium nuclei with a trace of heavier species. Radiation still dominates the energy content and particles remain immersed in a dense bath of photons. As expansion proceeds, the average energy of the photons continues to fall. The sea of radiation cools steadily as space grows. The pressure from this radiation influences how quickly the universe expands, and the balance between radiation and matter shifts gradually as the temperature drops. While radiation dominates the behavior of the universe, it is governed largely by the properties of this hot photon gas. Later, when matter becomes more important, the pattern of expansion changes. In the early stage covered here, however, the picture is that of a bright, dense universe whose properties are set by the interplay between light and particles in a nearly uniform environment. On large scales, the expansion is the same everywhere. No point in space is selected as a special center. Instead, every observer, if one could exist at that time, would see other regions moving away in all directions as space stretches. This uniform expansion carries the fireball into a smoother, cooler state without introducing strong directional differences. The tiny initial irregularities remain small, merely carried along and slightly amplified by gravity. Locally, collisions keep matter and radiation close to thermal equilibrium. The distribution of photon energies follows a simple pattern described by a temperature, and the particles share that temperature through rapid interactions. When the universe is dense, this equilibrium holds well. As density drops, equilibrium becomes harder to maintain, but in the hot early phase, scattering is frequent enough that the fireball can be described by smooth thermodynamic quantities, such as temperature and density, that vary slowly from point to point. Over tens of thousands to hundreds of thousands of years, the temperature falls from extremely high values toward levels at which new processes become possible. The light that once had energies high enough to break apart any atom gradually loses strength. The wavelengths of the photons stretch into ranges that are less destructive for bound states. At the same time, the frequency of collisions declines, and the tight coupling between matter and radiation begins to weaken. The fireball thins out not by fading to nothing, but by becoming more diffuse and less strongly interacting. Throughout this period, gravity works quietly in the background. Wherever the density of matter is slightly higher than average gravity slows the local expansion by a small amount and helps material cluster just a little more. Where the density is slightly lower, expansion proceeds a bit more freely. These differences are tiny at first, but they set the stage for later growth of structure. In the phase described here, they do not yet produce separate objects like galaxies or stars. Instead, they exist as gentle ripples in the density field, superimposed on a dominant smooth background of radiation and hot plasma. The overall behavior remains that of a nearly homogeneous expanding medium. The concept of a smooth fireball thinning out captures this balance between uniformity and slow change. The universe starts in a state where matter and light are densely packed and tightly coupled. As space expands, the temperature and density drop interactions become less frequent and the radiation field softens. Light travels across space in straight paths unless gravity bends it. As the universe expands, the space that light crosses also stretches. When light set out long ago, its waves had certain lengths. Over time, as expansion continues, the distance between wave crests grows. The light that first left a distant source at shorter wavelengths reaches an observer at longer wavelengths. Astronomers describe this change as redshift, because the light is shifted toward the redder, longer wavelength side of the spectrum. For very nearby objects, this effect is small. For sources that are far away in space and far back in time, the effect is large and moves their light out of the visible range into the infrared. The James Webb Space Telescope is designed around this fact. Its mirrors, sunshield, and instruments are built to detect faint infrared light that carries information from distant galaxies and other objects whose emission has been stretched by cosmic expansion. The observatory does not change the light. It receives whatever reaches it. In deep space, a photon that began its journey as energetic ultraviolet light can arrive at the telescope as gentle infrared light. The instruments must be cool, sensitive, and tuned to these longer wavelengths to record such signals. Infrared light is simply light with wavelengths longer than those that the human eye can see. It includes radiation from warm dust, cool stars, brown dwarfs, and planets, as well as the stretched light from very distant galaxies. Because the detectors on board the James Webb Space Telescope respond to infrared wavelengths, they can register both kinds of sources. The observatory acts as a collector for any infrared photon that enters its field of view, no matter whether that photon comes from the outer parts of the Milky Way or from a galaxy seen when the universe was very young. To make sense of the recorded data, astronomers later separate these possibilities using measurements of color and spectrum. The concept of redshift links distance, time, and wavelength in a single quantity. A higher redshift means that the universe has expanded by a larger factor since the light left its source. It also means that the light has been traveling for a longer time before reaching the telescope. In practice, astronomers estimate redshift in more than one way. In some cases, they use detailed spectra where light is spread into many narrow wavelength bins and fine features can be seen. In other cases, especially for very faint sources, they use measurements of brightness through several broad filters and compare the pattern of colours to theoretical models. The James Webb Space Telescope supports both approaches. Its cameras record images through several filters in the near-infrared and mid-infrared range. Its spectrographs spread light out to show how brightness changes smoothly or sharply with wavelength. The expansion of the universe has another effect that is important for these observations. As space expands, not only does light stretch, but the rate at which photons arrive also changes. Light from a very distant source appears dimmer than light from a closer one with the same intrinsic power. This dimming is not due to absorption, but to geometry and expansion. Photons are spread over a larger area as they travel and are received less frequently. To detect them, the telescope must collect light for long periods. That is why many programs with the James Webb Space Telescope use deep exposures, sometimes lasting many hours on a single field. During such long integrations, the detectors count photon after photon from faraway galaxies or from faint, cool bodies in the Milky Way. The infrared instruments must distinguish these weak signals from the background produced by the telescope itself and by any remaining stray light. Keeping the observatory cold helps reduce this noise. The large mirror area helps increase the rate at which useful photons are captured. Together, these design choices allow the telescope to measure light that has been travelling through space since a very early time in cosmic history. At the same time, the sensitivity to infrared wavelengths means that nearby cool objects that emit most of their energy in this range also stand out. Brown dwarfs, which are bodies more massive than planets, but not massive enough to sustain long-term nuclear fusion, shine mainly in the infrared as they cool over time. Dusty regions in the Milky Way radiate in similar bands. For the observatory, there is no difference in the way these photons are collected. Only the later analysis, based on wavelength patterns and apparent brightness, reveals whether a detected point of light is likely to be a distant galaxy, at high redshift, or a comparatively nearby cool object. Because light from different sources can end up with similar infrared colours, after passing through various physical processes, some objects can mimic others in deep surveys. A very distant young galaxy, whose light has been strongly redshifted, might have similar colour measurements to a cool brown dwarf with particular atmospheric properties in the outer parts of the Milky Way. For this reason, astronomers use both imaging and spectroscopic data to separate possibilities. They rely on the precise response of the filters and detectors on the James Webb Space Telescope and on careful models of how different types of sources should look in infrared light. The general behaviour of redshift and infrared emission provides the foundation for this work. Every photon that reaches the observatory carries information about the expansion of space since it was emitted and about the physical conditions at its point of origin. By measuring how much the light has been stretched and how bright it appears at different wavelengths, astronomers can estimate how far away the source is, how long ago it emitted the observed light, and what processes may be shaping its spectrum. All of these tasks depend on a clear understanding of how cosmic expansion affects light, and on instruments that can measure infrared wavelengths with high sensitivity and stability. Within this framework, the James Webb Space Telescope operates as a tool for turning faint redshifted signals into quantitative information about distant galaxies and nearby cool objects alike, using infrared light as the main channel of communication between these sources and the present-day observatory in deep space. In the planning rooms on Earth, teams select small parts of the sky for long, careful study. One of these efforts is called the Cosmic Evolution Early Release Science Survey. It uses the James Webb Space Telescope to look at a narrow strip of sky for extended periods, building a detailed picture that goes deeper than ordinary observations. From the vantage point at the second Sun-Earth Lagrange point, the telescope turns toward this field and holds steady. On the detectors, the chosen region is just a rectangle filled with tiny points and faint smudges. In space, it is a volume that extends across billions of light-years and contains galaxies, stars, gas, and dark matter. The survey design makes use of Webb's strength in the infrared. Rather than taking a single image, the telescope gathers a set of images through several different filters. Each filter passes light within a particular range of wavelengths and blocks the rest. The main near-infrared camera, known as the near-infrared camera or NIRCam, repeats the exposure of the same field with filter after filter. In each exposure, photons from distant and nearby sources fall onto the detectors, and their arrival is counted. Over time, with repeated visits and long integrations, the signal from very faint objects builds up. The resulting dataset is not just a picture in one color, but a stack of images, each showing the field as seen in a different band of infrared light. When astronomers later examine these stacked images, they measure how bright each source appears in each band. For many galaxies, the brightness changes smoothly across the filters. For some objects, the brightness rises sharply in certain bands and drops below the detection limit in others. These patterns give clues to the distance, age, and physical nature of the sources. The survey strategy is to cover a modest area to a great depth, rather than a very large area more shallowly. This means that the field is small on the sky but rich in information. It contains thousands of galaxies at different distances, as well as stars and compact objects within the Milky Way. Because the field has been observed previously by other telescopes, including the Hubble Space Telescope and ground-based observatories, there is already a base of knowledge about many of the sources within it. Webb extends this knowledge by adding much deeper and redder views, reaching objects that were either invisible or barely detected before. The scheduling of the survey must respect the constraints of the observatory. The field is placed in a region of the sky that the telescope can access safely with its sunshield in the correct orientation. Observations are broken into segments that fit within available windows. Each segment uses a combination of short and long exposures, along with dithers, which are small shifts in pointing. These small shifts allow gaps between detector elements and bad pixels to be filled in when the images are later combined. The results are mosaics in which each point in the sky has been sampled multiple times by different parts of the detector. Along with imaging, some survey programs include spectroscopic follow-up. For selected objects, the near-infrared spectrograph collects light and spreads it into spectra. In the early stages, however, the main task is photometry, which is the measurement of brightness through the set of filters. The Sears field thus becomes a catalogue of sources with measured fluxes at several wavelengths. Each entry contains positions on the sky and brightness values in each band. This catalogue is the starting point for identifying candidates for more detailed study. Astronomers use it to search for objects that could be very distant galaxies based on sudden changes in brightness between adjacent filters that mark the redshifted absorption of hydrogen. They also use it to look for objects whose colours match those expected for cool brown dwarfs within the Milky Way. The same imaging data serve both purposes. The field itself has no special visual features. It is chosen primarily for practical reasons such as low contamination by bright foreground stars and a location that has been well studied before. In images, it appears as a dense scattering of small sources, most of them unresolved or barely resolved at the depths reached by Webb. Yet within this crowd, the combination of deep exposures and many filters reveals subtle differences. Some sources vanish entirely in the shorter wavelength bands, but emerge clearly in the longer ones. Others follow colour sequences known from stellar populations and substellar objects. The careful uniform observing pattern of the survey makes it possible to compare these sources in a consistent way. The data processing pipeline on the ground turns raw detector readouts into calibrated images. It removes instrumental signatures, corrects for distortions, and aligns all exposures to a common coordinate system. Background levels are estimated and subtracted. Once this is done, software searches the images for peaks that rise above the noise. For each detected source, the system measures how much light falls within a chosen aperture in each band. Human teams then inspect and refine these measurements, checking for artifacts, overlapping sources, and other issues that might affect reliability. Over time, the Sears field becomes more than just a set of pictures. It is a structured collection of measurements that can be queried and analysed. Researchers can select objects with certain colour criteria, apparent brightness or shapes, and can cross-match with previously known sources. The survey provides a common reference point for studies of galaxy evolution, the distribution of distant objects, and the census of cool brown dwarfs and other substellar bodies in the line of sight. Because the data cover many wavelengths in the near-infrared, the field is especially suited to finding sources whose light has been strongly affected by redshift or by low temperatures. The Sears field demonstrates how the James Webb Space Telescope operates not just as a camera, but as a survey instrument. Through a planned sequence of deep overlapping exposures in multiple filters, it builds a detailed map of a small region of the sky. This map is rich enough to support many scientific questions at once, from the assembly of galaxies over cosmic time to the properties of faint objects within the Milky Way. It is within this kind of carefully observed field, with its dense catalogue of measured sources, that puzzling objects first stand out as points of light, with unusual combinations of brightness and colour. Within the deep survey field, the near-infrared camera on board the James Webb Space Telescope works methodically. It views the same patch of sky through several filters, each passing a different slice of infrared wavelengths. In the case of the field that includes the object later called Capotaro, the camera collects images at 7 distinct wavelength ranges in the near-infrared. For most sources in the field, these 7 views form a simple pattern. A galaxy or star that is bright in one band is usually also visible, though fainter or brighter, in nearby bands. The brightness may rise or fall gradually from one filter to the next, but the object remains present across much of the sequence. When the images are aligned and examined together, each source appears as a set of detections that trace out its behaviour with wavelength. For Capotaro, the pattern is different. In the shorter wavelength bands, where many galaxies and stars are clearly seen, this object does not stand out. As astronomers later measure fluxes in the calibrated images, they find that the source is not significantly detected in the first several filters. When they inspect the 2 longest wavelength bands, however, the object becomes visible as a compact point of light. It appears bright in these reddest filters, even though it was effectively absent in the bluer, near-infrared images. The result is a sharp contrast non-detections in multiple bands, followed by clear detections in the final 2. This behaviour marks Capotaro as an outlier relative to typical sources in the catalogue. The measurement process that leads to this conclusion is careful and structured. After the raw images are corrected for instrumental effects and combined into Mosaic software searches for peaks above the noise. In the longest wavelength images, the detection algorithm identifies a point-like source at a specific position in the field. That position is then checked in each of the other bands. Apertures are placed at the same coordinates, and the total recorded counts are measured with corrections for background levels and detector characteristics. In most of the shorter wavelength bands, the measured values are consistent with noise leading to upper limits rather than firm brightness values. In the longest bands, the counts exceed the threshold, producing reliable flux measurements with associated uncertainties. From these measurements, astronomers build a simple spectral energy distribution, which is a plot of brightness against wavelength. For Capotaro, this distribution shows negligible or undetected flux in the shorter near-infrared bands and significant flux in the 2 longest ones. On such a plot, the points for the shorter wavelengths lie low or appear only as arrows indicating limits, while the points for the longest wavelengths rise well above the noise. The overall shape resembles a step with a sudden increase between neighbouring filters. This shape is not what is seen for most ordinary galaxies or stars at moderate distances. It suggests that some process is strongly suppressing the observed light at shorter wavelengths, or that the intrinsic emission is concentrated at longer wavelengths. The near-infrared camera provides only the measurements. It does not decide which physical explanation is correct. The properties of the filters matter for interpreting these data. Each filter has a central wavelength and a width over which it is sensitive. The 7 filters used in this part of the survey cover a range that begins at shorter, near-infrared wavelengths and extends to the redder side where the detectors still respond. The approximate positions and widths of these filters are known precisely so astronomers can compare the pattern of detections and non-detections to models of different types of sources placed at different distances. The sharp change in Kappa Tauro's brightness between adjacent filters indicates that some spectral feature such as a strong break or an absorption edge lies between those bands in the observed frame. This is an important clue, but at this stage of analysis the focus is on the measurements themselves, which filters show a detection, how strong it is, how robust the non-detections are, and how the uncertainties combine. In the context of the full Sears catalogue, Kappa Tauro stands out when sources are plotted in colour-colour diagrams. These diagrams show one colour defined as the difference in brightness between 2 filters against another colour from a different pair. Ordinary galaxies populate broad sequences in these plots, and stars in the Milky Way fall into their own regions. Cool brown dwarfs and other substellar objects occupy areas that reflect their complex infrared spectra. Kappa Tauro's strong flux only in the reddest bands gives it extreme colours that place it away from the bulk of the population. This makes it a candidate for closer inspection within the survey data. It is not the only unusual source in the field, but its combination of brightness in the longest wavelengths and non-detection in the shorter ones is rare in the survey area. The imaging data alone already show that whatever this object is, it does not match the simple patterns of more common sources. To confirm that the detection is real and not an artifact, the team checks several aspects of the images. They examine the individual exposures that went into the mosaics, verifying that the source appears consistently in the reddest bands and that its position is stable. They look for signs of cosmic rays detector flaws or residual background structures that might mimic a point source, and they verify that the point-like profile of the object matches that expected for a compact source at that location on the detector. They also check that there are no nearby bright objects whose light could have been scattered or misassigned. These tests increase confidence that the measured fluxes are associated with a real astrophysical source. Once the imaging measurements are secure, they define how Kappa Tauro appears in the near-infrared camera observations. The 7-band photometry describes a compact point in the Sears field that is effectively invisible in the shorter near-infrared filters and clearly present in the 2 longest ones. This description, expressed entirely in terms of observed brightness and colour across the camera's filters, is the complete view that the imaging data provide of Kappa Tauro at this stage, setting out the measured properties, while the focus remains on the photometric record itself. In the deep survey data from the Cosmic Evolution Early Release Science field, Kappa Tauro first appears not as a striking picture, but as an entry in a table. Astronomers working with the near-infrared camera images are looking for very old galaxies objects whose light has been stretched so strongly by cosmic expansion that most of their emission has moved into the longest near-infrared wavelengths. For these candidates, one pattern is common little or no detectable light in the shorter near-infrared filters, followed by a clear appearance in the redder bands. As the team searches the catalogue, they apply selection rules based on this idea. They ask which sources are absent in early filters, but present in later ones, and set thresholds to avoid spurious detections. Among the many thousands of faint points, Kappa Tauro stands out. Its measured brightness is low and consistent with noise in the first several filters, but in the final two longest wavelength bands, it is clearly detected as a compact source. When placed on colour plots that compare brightness differences between filters, it sits far from the crowded regions where most galaxies and stars appear. It occupies part of the diagram where very distant galaxies and very cool nearby substellar objects can both lie. This simple fact turns a promising selection into a puzzle. The light that the near-infrared camera has recorded from Capitauro could belong to a galaxy seen when the universe is very young, or to a brown dwarf whose atmosphere shapes its spectrum into a similar form, or to some other rare configuration. The imaging alone does not specify which. The team notes its unusual properties and assigns it an internal label. The working name Capitauro is attached to a set of coordinates in the sky brightness measurements in 7 bands and estimates of how reliable the detections and non-detections are. At this stage, the object is one among a small group of interesting candidates flagged for further attention. The earlier data available on this region had already hinted at something unusual at this position, but those earlier observations lack the combination of depth and wavelength coverage now provided by the James Webb Space Telescope. With the newer images, the view is clearer yet still incomplete. The sudden appearance of Capitauro only in the longest wavelength bands is now confirmed rather than suspected, and the strength of its detection in those bands can be measured with better precision. The field around it is checked carefully. Nearby sources are examined to see whether any confusion or blending might be affecting the photometry. The point-like shape of Capitauro in the reddest images is compared to the expected profile of distant compact sources and to that of stars in the field. These checks support the conclusion that the measured light comes from a single isolated object, not from an artifact or a blend. With this assurance, the team begins to treat Capitauro as one of the most puzzling sources in the survey. They compute simple estimates under different assumptions. If the object is taken to be a galaxy with its light cut off at shorter wavelengths by hydrogen absorption at very high redshift, then its observed brightness in the reddest bands implies a large intrinsic luminosity. If the same measurements are instead interpreted with models of very cool brown dwarfs at the edge of the Milky Way, the required temperature and distance push against the known limits of that population. Either way, the numbers fall in ranges that would make Capitauro an extreme case. In both interpretations, it does not sit comfortably within the ordinary distributions of known galaxies or brown dwarfs. These early calculations are not final results. They are indicative numbers meant to show which broad possibilities are plausible. They guide the next steps by revealing that Capitauro is not just another high redshift candidate or just another cool substellar object. It seems to challenge expectations in whichever category it is placed. Because several scenarios remain open, the team avoids declaring a firm identity. Instead, they list this object as a prime target for more detailed study. Within the wider analysis of the survey, Capitauro is one entry in a longer list of candidates, but its unusual combination of non-detections and strong detections, its position in colour space, and its implied properties under different models give it a special status. It is marked as a source where additional information beyond the 7-band photometry will be needed to narrow down its nature. For now, the description of Capitauro remains anchored to what the imaging data show: a compact point in the Sears field, invisible in several near-infrared filters and bright in the 2 longest ones located in a region of colour space, shared by very distant galaxies and very cool nearby objects, and carrying brightness values that in any interpretation place it near the edge of what current models consider common. After the near-infrared camera images have revealed Capitauro as an unusual point of light, attention turns to the spectrograph. On board the James Webb Space Telescope, the near-infrared spectrograph, or NIR spec, is designed to take the light from selected sources and spread it out into a spectrum. Instead of a single brightness value for each filter, a spectrum provides a series of measurements across a continuous range of wavelengths. For bright and well-sampled objects, this reveals detailed structures, gentle slopes, sharp breaks, and possible emission or absorption features. For very faint sources, the spectra are often noisy, but even then they can give more fine-grained information than imaging alone. In the case of Capitoro, the available NER-spec data are limited, but they add an important layer. To obtain them, the telescope is pointed again at the field this time, with the spectrograph configured to place a small aperture on the position of the object. Light from Capitaro passes through this aperture and into the instrument, where dispersing elements separate it by wavelength before it falls on the detectors. Over the exposure, photons arrive irregularly, and the spectrograph records their distribution as a faint trace. Once the observation is complete and the data are transmitted to Earth, this trace is processed. Calibration steps correct for instrumental effects and map each detector position to a physical wavelength. Background levels are estimated and subtracted, leaving the net signal from the target. The result is a spectrum that shows how the recorded brightness varies as a function of wavelength over the range covered by NER-spec. Because Capitaro is faint, the spectrum is noisy. The signal rises above the noise in some parts and sinks back into it in others. There are no sharp, high-contrast lines that would immediately fix its nature, but there is still structure. The overall slope, the presence or absence of strong breaks, and the relative levels in different wavelength intervals provide clues to the temperature and possible redshift of the source. These clues are subtler than in the ideal case, yet they are more informative than photometry alone. In practice, the team does not look at the spectrum in isolation. They place it alongside the 7-band NERCam measurements, aligning the wavelength scales so that the imaging points and the spectral curve can be seen together. The broad filters of NERCam sample the spectrum at wide intervals, while NERSpec fills in some of the spaces between them with finer resolution. Where the imaging has shown a sharp rise in brightness between neighbouring filters, the spectrum can reveal whether this is due to a true break in the source's emission, a smooth slope, or the combined effect of several smaller features. Even if individual spectral features are not detected at high significance, the overall shape of the continuum still carries information. The NERSpec data are also used to refine the estimates of how much light Capitaro emits at each wavelength. Imaging provides integrated fluxes over the filter bandpasses, but the exact distribution within those bands matters when models are applied. By comparing the spectrum and the photometric points, the team can check for consistency and adjust for any mismatches. For example, if the spectrum suggests that the true flux is slightly higher or lower in part of a filter's range, this can be taken into account when fitting models to the combined data. The spectrograph's sensitivity to fine variations also helps in constraining temperature. Objects with different effective temperatures have different spectral shapes in the near-infrared. A very hot young stellar population in a distant galaxy produces one type of continuum. A cool brown dwarf with complex molecular absorption in its atmosphere produces another. Although both can give similar colours when measured only in broad filters, their detailed spectra differ. For Capitaro, the limited NERSpec measurements do not capture every expected feature at high confidence, but the general distribution of flux with wavelength can still support or disfavour certain temperature ranges. In the same way, redshift leaves its mark on the spectrum. As light is stretched by cosmic expansion, features that originate at known wavelengths are shifted to longer wavelengths. A strong drop at the wavelength corresponding to hydrogen absorption in the rest frame, if present, would move to a predictable location in the observed spectrum for a given redshift. When the data are examined, astronomers look for any sign of such breaks or changes. In the case of Capitaro, the quality of the spectrum does not allow a single precise value of redshift to be read directly from a clear feature, but it does permit ranges to be tested. Some redshifts would place expected breaks or lines in parts of the spectrum where no significant structure is seen. Others would be more compatible with the observed pattern, even if the evidence remains modest. The near-spec observation thus becomes a way to remove some possibilities while leaving others open. The data show that certain combinations of temperature and redshift would be inconsistent with the measured spectrum even given its noise. Other combinations remain compatible. The role of the spectrograph here is not to give a simple answer but to refine the space of allowed solutions defined by the imaging. It transforms the view of Capitaro from 7 broad points into a more continuous though still faint curve. Throughout this process, the limitations of the data are kept in mind. The exposure time, the faintness of the source, and the characteristics of the instrument mean that many subtle features, if they exist, lie below the detection threshold in this initial observation. The team therefore avoids drawing strong conclusions from any single bump or dip in the spectrum. Instead, they focus on the overall trend, the consistency between NR-spec and NR-cam, and the degree to which simple models can or cannot reproduce the joint dataset. In the working description, the near-spec observation of Capitaro is characterized as a finer but still incomplete picture of its light. It provides more detailed sampling of the near-infrared wavelengths, where the object is bright confirms the general level of flux indicated by the imaging, and offers a way to test broad categories of temperature and redshift. It does not by itself fix the identity of the source. Together with the 7-band imaging, however, it forms a more comprehensive record of how Capitaro's light is distributed in the near-infrared setting, the stage for model comparisons that will explore which physical scenarios best match the combined measurements, while remaining consistent with the limits imposed by these early spectra. With both imaging and spectra in hand, the task shifts from collecting light to interpreting it with models. The data for Capitaro consist of 7 measurements from the near-infrared camera, including non-detections in several bands and clear detections in the 2 longest ones, together with a faint but calibrated spectrum from the near-infrared spectrograph across part of the same wavelength range. To learn what kinds of objects could produce such a distribution of light, astronomers construct a set of model spectra and compare them directly to the observations. Each model represents a different physical scenario. Some models describe galaxies at various stages of growth and at different redshifts. Others describe brown dwarfs with specific temperature, surface gravities, and atmospheric compositions. Additional options include rare types of young galaxies and unusual planetary mass objects with distinctive spectral signatures. The goal is not to test every possible configuration in detail, but to survey the main classes that could reasonably generate the observed pattern of brightness and colour. For galaxies, the models combine stellar populations, gas and dust. They specify how many stars of different masses and ages are present, how much gas remains, and how that gas absorbs and re-emits light. The light from these model galaxies is then shifted to different redshifts, accounting for the expansion of the universe. This shift moves features such as the hydrogen break and emission lines to longer wavelengths. Once shifted, the model spectra are passed through the same filter responses that define the near-infrared camera bands, and the expected brightness in each filter is computed. In parallel, the models are sampled at the wavelengths covered by the near-infrared spectrograph. This yields synthetic photometry and synthetic spectra that can be compared directly with the measurements for Capitaro. For brown dwarfs, the models include detailed atmospheric physics. They take into account the temperature structure, the presence of molecules such as water vapor and methane, and the formation of clouds. These factors shape the infrared spectrum through broad absorption bands and emission peaks. By varying the effective temperature, surface gravity, and composition, the models produce a range of spectral energy distributions. As with the galaxy models, these brown dwarf spectra are passed through the camera filters and sampled at the spectrograph wavelengths to produce predicted photometry and spectra. The comparison between models and data proceeds through statistical measures. For each model, the predicted brightness values in the 7 filters and at the spectral sampling points are matched against the observed ones with allowances for measurement uncertainties. A goodness of fit statistic such as a chi-squared value summarizes how well the model reproduces the combined dataset. Models that strongly disagree with the observations, for example, by predicting significant flux in filters where Kappa Tauro is not detected, or by failing to match the sharp rise between the last two bands, receive poor scores and are discarded. Models that come closer are kept for further examination. Because the data include both detections and upper limits, the fitting process must treat them carefully. Non-detections in the shorter wavelength bands do not mean that the true flux is exactly zero. They mean that any flux present lies below a certain threshold. The models must therefore avoid predicting brightness above these thresholds, but small amounts of light in those bands cannot be ruled out. Similarly, the uncertainties in the detected fluxes and in the spectrum mean that an exact match is neither expected nor required. The goal is to identify regions of parameter space where the models remain consistent with the data within the stated errors. As the analysis proceeds, it becomes clear that many simple configurations are incompatible with the observations. Ordinary galaxies at moderate redshift with typical star formation histories and dust contents tend to produce too much light in the shorter wavelength bands or spectra that do not rise sharply enough toward the reddest filters. Many standard brown dwarf models also struggle either because they are too bright at shorter wavelengths or because their spectral features produce patterns in the near-infrared spectrograph range that do not align well with the faint trace seen for Kappa Tauro. These mismatches help narrow the field. At the same time, the data are not precise enough to single out one model as the clear best explanation. Several combinations of parameters in the galaxy family and in the brown dwarf family remain compatible with the measurements. Some galaxy models at very high redshift with particular star formation histories and dust properties can match the steep rise in brightness between the filters and the overall level of flux in the reddest bands, while staying below the detection limits in the bluer ones. Some brown dwarf models with very low effective temperatures and specific atmospheric structures can also reproduce the observed colours and the rough shape of the spectrum. The team also tests more exotic scenarios, such as a very unusual young galaxy with atypical emission line strengths or a rare type of planetary mass object. These possibilities are not favoured by simple population arguments, but they are checked to see whether any provide a significantly better match to the data. In practice, none of these alternative models offers decisive improvement over the main galaxy and brown dwarf scenarios. The overall result of the modelling stage is therefore not a firm identification, but a filtered set of possibilities. The analysis shows that Kappa Tauro is unlikely to be an ordinary galaxy at moderate distance, or a typical brown dwarf with well-studied properties. It also shows that several carefully tuned high redshift galaxy models and several extreme brown dwarf models can each provide an acceptable fit to the combined near-infrared camera and near-infrared spectrograph data. Among all the tested options, two broad interpretations remain the most viable: that Kappa Tauro is a very early massive galaxy at high redshift, or that it is a very cold brown dwarf in the outer regions of the Milky Way. At this point, the modelling has reached the limit set by the present data quality. The current observations do not distinguish sharply between these two classes. They allow both to exist in the space of solutions with different sets of parameters, while excluding many other possibilities. The description of Kappa Tauro after this stage is that of a source whose measured light can be matched either by a distant young galaxy model or by an extreme brown dwarf model with no single scenario yet demanded by the evidence. When Kappa Tauro is treated as a galaxy at extreme distance, the measurements from the near-infrared camera and the near-infrared spectrograph suggest a picture that sits near the edge of current expectations for the early universe. In this interpretation, the sharp rise in brightness between the shorter and longer near-infrared filters and the overall level of flux in the reddest bands are explained by a very large redshift. The strong suppression of observed light at shorter wavelengths is taken to mark the point where hydrogen in the early universe absorbs radiation in the rest frame, a feature that moves to longer wavelengths as redshift increases. Placing this break at the position indicated by the data leads to an estimate that the light left Capotaro when the universe was only about 100 million years old, a small fraction of its present age. At such an early time, standard models predict that galaxies are just beginning to assemble. They expect small systems with relatively low stellar masses to dominate. When the same models are adjusted to fit the brightness of Capotaro in the reddest bands at this high redshift, they require a large intrinsic luminosity. Converting this luminosity into a stellar mass under reasonable assumptions about the types of stars present produces values of more than 1 billion times the mass of the Sun. This is not a precise single number. It is a range that depends on choices for the star formation history, the distribution of stellar ages and the amount of dust, but across many model combinations the required mass remains large. The result is that Capotaro in the early galaxy scenario appears as a massive system that has already assembled a significant amount of stellar material at a time when the universe is still very young. Comparing the inferred age of the universe at this redshift to the estimated ages of previously known record-holding galaxies highlights why this scenario is notable. Earlier candidates for the most distant galaxies discovered with other instruments and with early James Webb observations typically lie at times when the universe is a few 100 million years old. If Capotaro truly sits at a redshift corresponding to about 100 million years after the Big Bang, it would push the appearance of a very massive galaxy back by roughly 200 million years relative to those records. In the language of observations, it would be among the earliest known galaxy candidates, and possibly the one whose light comes from the shortest time after the beginning of cosmic expansion. The calculations that lead to these statements are built on the observed brightness, the assumed cosmology, and the model spectra used to convert flux into intrinsic properties. They are not independent measurements of mass and age in the way that some nearby galaxy studies can be. Instead, they are inferences that rely on the idea that the spectrum of a young galaxy, with certain characteristics when shifted to high redshift, can match the photometry and the noisy spectrum recorded for Capotaro. Within this framework, the high redshift solution produces consistent fits and places the object in the early universe with substantial stellar mass. The team is careful to state that this interpretation is a possibility, not a settled fact. The data are compatible with an early massive galaxy, but they do not rule out other explanations. The uncertainty arises from several sources. The near-infrared spectrograph data are limited in depth and resolution, so key features that could fix the redshift more precisely are not detected at high significance. The photometry in the bands where Capotaro is not seen provides only upper limits, which allow a range of true flux levels below the detection threshold. The models used to convert observed light into physical properties carry their own uncertainties in how they treat star formation dust and the initial distribution of stellar masses. Small changes in these inputs can shift the inferred stellar mass and age. In addition, the high redshift galaxy interpretation must be considered in the context of how many such objects are expected to exist. If many galaxies with masses above 1 billion solar masses are already present 100 million years after the Big Bang, this might strain some current models of structure formation which predict slower assembly of large systems. If only a few exist rare but possible, then Capotaro could be one of these uncommon early massive galaxies. At present, the observations of Capotaro alone do not determine how frequently such objects occur. They only show that under the galaxy scenario, this particular source would occupy an extreme position in mass and time. Another aspect of the early galaxy picture concerns the size of the emitting region. At high redshift, the angular size of a compact galaxy on the sky corresponds to a small physical scale. In the imaging data, Kappa Tau is unresolved, or only marginally resolved consistent with a compact system. Under the high redshift assumption, this compactness suggests a dense configuration of stars and gas concentrated into a relatively small volume. The exact size is difficult to determine from the present images, but the combination of high luminosity and small apparent size implies a high surface brightness in the rest frame. This too places the object among the more intense star-forming systems known in the early universe. The early galaxy interpretation is recorded in the study as one of the main possibilities supported by the current data. The authors report that when they fit galaxy models to the combined near-infrared camera and near-infrared spectrograph measurements with redshift as a free parameter, they consistently find solutions in which Kappa Tau lies at very high redshift and formed about 100 million years after the Big Bang. They note that these solutions require a large stellar mass on the order of, or above, 1 billion solar masses, and acknowledge that such a result, if confirmed, would extend the known timeline for massive galaxy formation. At the same time, they emphasize that the data do not allow them to rule out alternative models. The interpretation remains conditional. Kappa Tau may be a very early massive galaxy, but the evidence is not yet strong enough to assign this identity uniquely. The description of Kappa Tau at this stage under the early galaxy scenario is therefore that of a candidate system at extreme redshift, with inferred formation about 100 million years after the Big Bang large stellar mass, above 1 billion solar masses compact apparent size and brightness, that would make it one of the most distant and massive known galaxies. If this solution is correct, all presented with the clear note that its status as the oldest galaxy is only a possibility and not yet established. If Kappa Tau is a very early massive galaxy, its outer structure is not directly resolved in the current images, but models guided by the data suggest a compact system embedded in a larger halo of matter and gas. In this picture, the visible light recorded by the James Webb Space Telescope comes from stars and hot gas gathered within a region too small to show clear shape in the seer's images, while an extended envelope of dark matter and more diffuse material surrounds it. The dark matter halo is an invisible framework whose gravity holds the galaxy together. Simulations of structure formation indicate that at such an early time, halos that host galaxies with stellar masses of more than 1 billion solar masses must already have collected large amounts of matter from their surroundings. Their total mass, including dark matter, would be much higher than the stellar mass alone. Within this halo, gas from the intergalactic medium falls inward along filaments and streams, cooling as it settles. This gas supplies the fuel for star formation in the central regions, where the light detected by the near-infrared camera originates. The boundary between the halo and its surroundings is not sharp. Instead, the density of dark matter and gas gradually declines, with distance from the center linking the galaxy to the growing cosmic web around it. In the early universe, the gas within and around such a halo is likely still partly neutral and partly ionized. The first generations of stars produce intense ultraviolet radiation that ionizes hydrogen in their immediate vicinity, carving out bubbles of ionized gas. In the Kappa Tau galaxy scenario, these bubbles would expand within the halo and possibly into the surrounding medium. Their presence affects how easily light can escape. Photons with energies capable of ionizing hydrogen are absorbed or scattered until they reach regions where the gas has been cleared. The resulting pattern of absorption creates breaks in the spectrum, which when shifted by redshift contribute to the observed sharp drop between filters in the near-infrared camera data. The outer regions of the galaxy near the edge of the halo may contain streams of gas that have not yet fully joined the central body. These streams can be clumpy and irregular, carrying both pristine hydrogen and helium, and material that has already been enriched by previous generations of stars. In the very early phase implied by the high redshift interpretation, much of this gas would still be relatively simple in composition, with only small amounts of heavier elements. However, if star formation has already proceeded rapidly in the central regions, winds and supernovae could drive enriched material outward, mixing heavier elements into the halo gas. This mixing changes cooling rates and influences how new stars form in the outer parts. The distribution of starlight in such a young galaxy is expected to be strongly peaked toward the center, where gas densities and star formation rates are highest. The near-infrared camera sees Capitaro as a compact point because the bright inner part dominates the emission, and because the angular resolution at this distance is limited. Under the early galaxy interpretation, the unresolved profile would correspond to a physical size of only a few hundred to perhaps a few thousand light-years, depending on the exact redshift and lensing effects, if any. Within this region, the combined light of many stars of different masses produces the continuum observed in the Redis filters. The outer stellar component, if present, would be faint and difficult to detect against the background noise in the current data, so the images mostly record the central concentration. Around the main stellar body, the halo may also host smaller substructures. These could include satellite clumps where star formation has begun on a smaller scale, or gas-rich fragments that are still collapsing. In standard models, early massive galaxies grow not only by forming stars in place, but also by merging with and accreting these smaller systems. Each merger deposits stars and gas into the main body and can disturb its structure. However, at the distances implied for Capitaro, such details are far below the resolution and sensitivity of the present observations. The data therefore provide only the integrated light of the central region, without direct information on the distribution of satellites or the detailed shape of the halo. Even so, the overall framework from theory allows a consistent description, a dense central zone of star formation, embedded in a larger, gradually declining distribution of dark matter and gas. The outer parts of the halo also play a role in connecting the galaxy to its environment. Gas flows into the halo from the cosmic web, bringing fresh material for star formation and energy, and metals flow out from the central region through winds and radiation. These exchanges can influence how quickly the galaxy grows and how its surroundings evolve. In the early galaxy scenario for Capitaro, the inferred high stellar mass at such an early time suggests that inflow must have been efficient, delivering large amounts of gas to the central regions within a short cosmic interval. At the same time, feedback from massive stars and supernovae likely heats and stirs the halo gas, regulating further collapse. The balance between inflow and feedback determines how the outer structure develops, but the current data do not constrain this balance directly. They only show that the central regions are bright enough to imply vigorous activity. The shape of the spectral energy distribution also gives indirect hints about dust in the outer parts. If the galaxy contains dust grains formed in the atmospheres of massive stars or in supernova ejecta, these grains can absorb ultraviolet and optical light and re-emit it at infrared wavelengths. This process tends to redden the observed spectrum. In Capitaro's case, some level of dust may be required in the models to match the exact slope of the near-infrared continuum, but the data are not detailed enough to map where that dust resides. It could be concentrated in the central star-forming regions, or more spread out in the outer parts of the halo. Without spatially resolved images, only the integrated effect is visible. In summary, under the early galaxy interpretation, the outer structure of Capitaro is described as a compact luminous core surrounded by an extended dark matter halo, with gas flowing in from the environment, likely partial ionization around sites of active star formation, and possible dust mixed into the central and halo gas. The current James Webb Space Telescope observations do not resolve this structure directly. They provide a total light profile consistent with a small, bright central region and imply through models and theory the presence of a larger halo and outer gas that support and feed the growth of the galaxy in the early universe, while leaving the detailed shape and substructure of these outer regions uncertain. In the inner parts of Kappa Tauro, under the early galaxy interpretation, gas and stars share a small volume, where conditions are intense compared with many present-day galaxies. The light that reaches the James Webb Space Telescope in the reddest, near-infrared bands comes mainly from this compact region. It is the sum of many individual stars and clusters, whose combined emission forms the smooth continuum seen in the data. If the inferred stellar mass of more than 1 billion solar masses is correct, then a large number of stars are already in place by the time the observed light leaves the system, only about 100 million years after the beginning of cosmic expansion. Models of such an early massive galaxy suggest that much of its light is dominated by young massive stars. These stars burn their nuclear fuel quickly and emit strongly in ultraviolet and blue wavelengths in their own rest frame. As the universe expands, that light is shifted into the near-infrared where the James Webb Space Telescope detects it. The presence of many massive stars implies a high rate of recent star formation. Gas must be collapsing into new stars at a rapid pace, and this activity shapes the internal conditions. Within the central region, gas density is high. Clouds of hydrogen and helium with traces of heavier elements fragment into clumps as gravity overcomes internal pressure. In these clumps, stars form in groups rather than alone. Massive stars form alongside lower mass stars, and their energy output quickly begins to influence the surrounding gas. Intense radiation ionizes nearby hydrogen, creating small ionized bubbles around young clusters. Stellar winds push on the gas-driving flows and turbulence. Some very massive stars reach the end of their lives in only a few million years and explode as supernovae, sending shockwaves through the interstellar medium. These explosions release both energy and newly formed heavy elements into the surrounding gas, beginning the process of chemical enrichment. The first generations of stars in any galaxy form from gas that contains almost only hydrogen and helium. As more stars live and die, heavier elements such as carbon, oxygen, and iron accumulate. In Kappa Tauro, at such an early cosmic time, this enrichment is still in its early stages, but may already be detectable in the integrated properties. The models that match the near-infrared brightness often require some contribution from stars that are not entirely pristine, meaning that at least a modest amount of heavier elements is present. This affects how the gas cools, how new stars form, and how the spectrum looks when shifted to high redshift. Some of the heavy elements produced in massive stars condense into tiny solid particles known as dust grains. These grains absorb and scatter ultraviolet and optical light, and re-emit energy at longer wavelengths. In the inner regions of Kappa Tauro, dust mixed with gas can dim and redden the light from young stars. When this effect is combined with redshift, the result is a near-infrared spectrum whose slope depends on both the star formation history and the dust content. The models used to interpret the data include these effects in approximate form. They show that a small to moderate amount of dust can help reproduce the observed shape of the continuum, but the exact distribution of dust within the galaxy remains unconstrained by the current observations. The internal gas is likely turbulent. Gravitational instabilities, feedback from star formation, and inflows from the outer halo all stir the medium. This turbulence can create dense filaments and clumps where new stars keep forming, while also driving broader motions that redistribute material. In some scenarios, the central few hundred to few thousand light-years contains several bright star-forming clumps embedded in a more diffuse component. From Earth's point of view, these structures blend into a single unresolved point, but their presence can influence the time variation and spectral fingerprints of the galaxy. If star formation is very concentrated in a few regions, the light can be dominated by the youngest populations. If it is more spread out, somewhat older stars contribute more strongly. Another question concerns the presence of any central compact object such as a growing black hole. At early times, some galaxies already host black holes that accrete gas and produce additional radiation. This activity can leave signatures in the spectrum, including specific emission line patterns or excess high-energy light. For Kappa Tauro, the current near-infrared spectrograph data are not deep or detailed enough to reveal clear signs of such an active nucleus. The models used in the study focus mainly on stellar and interstellar contributions. A central compact object cannot be confirmed or ruled out with the present observations. It remains a possible but untested part of the internal structure. The radiation field inside the galaxy is strong where massive stars cluster. Ionizing photons create layers of ionized and neutral gas, and recombination processes emit characteristic lines in the ultraviolet and visible ranges in the rest frame. When redshifted, some of these lines may move into the near-infrared region covered by the spectrograph. The initial NIR spectrum of Kappa Tauro, however, is too noisy to show clear emission line peaks. What is recorded instead is mainly the continuum of starlight slightly shaped by any broad features that rise above or fall below the average level. This limits how precisely the internal conditions can be reconstructed, but it still allows general statements about strong star formation and early enrichment to be made. Gas in the inner regions may also be moving outward as galactic winds. Where many supernovae explode in a small volume, and radiation pressure from young stars is intense, gas can be pushed away from the central areas. These outflows can carry metal-enriched material into the outer halo, contributing to the gradual spread of heavy elements. The balance between inflow and outflow affects how long the central reservoir of gas can sustain high star formation rates. If outflows are strong, and the supply of new gas from the outer halo is limited, star formation might slow. If inflows keep pace with or exceed outflows, intense activity can continue for longer periods. In the Kappa Tauro galaxy scenario, the very high inferred stellar mass at such an early time suggests that inflow has so far been efficient. The current data do not provide direct measures of wind velocities or gas flows, so these processes are inferred from general models rather than from specific features in the spectrum. Within this compact system, the distribution of stellar ages is likely skewed toward youth. Many stars are only a few million to a few tens of millions of years old. Some lower mass stars that formed earlier remain on the main sequence, contributing steady light, while the most massive stars dominate the ultraviolet output. The integrated spectrum observed today after redshift combines all these contributions. When the models are fit to the data, they often favour star formation histories, in which a large burst of star formation has taken place relatively recently before the light now reaching the James Webb Space Telescope was emitted. In this sense, Kappa Tauro as an early galaxy is seen in a phase of rapid internal growth and active change. Overall, the inner conditions under the early galaxy interpretation can be summarized as those of a dense compact region with vigorous star formation, a prominent population of massive young stars' ongoing chemical enrichment, from supernovae, some dust mixed into the gas, and a strong internal radiation field, all confined within a small physical space embedded in a larger halo. The James Webb data do not resolve these structures directly, or measure each process separately, but through models they paint a consistent, though still uncertain, picture of a young galaxy building up its stellar content quickly in the first 100 million years after the Big Bang, with internal processes that are intense for its size and time, yet described cautiously as one of several possible ways to interpret the observed light from Kappa Tauro. In the alternative view, Kappa Tauro is not a distant young galaxy, but a member of the Milky Way, a very cold brown dwarf lying far from the Sun and glowing faintly in the infrared. A brown dwarf is an object more massive than the largest gas giant planets, but not massive enough to sustain long-term nuclear fusion of hydrogen in its core. It forms in a way similar to stars from the collapse of a gas fragment, but its mass does not reach the threshold needed to ignite stable hydrogen burning. After formation, it shines mainly by releasing stored heat cooling gradually over time. In this scenario, the light recorded by the James Webb Space Telescope from Kappa Tauro originates from such a substellar body smouldering at a low temperature and located at more than 7 light-years from the Sun in the outer regions of the Milky Way along this line of sight. The near-infrared camera measurements of Kappa Tauro bright in the 2 longest wavelength bands and undetected in the shorter ones can be matched by models of brown dwarfs with extremely low effective temperatures. These models show that as a brown dwarf cools to a few hundred kelvins, its emission shifts further into the infrared and molecular absorption bands in its atmosphere strongly shape the spectrum. The combination of thermal emission and absorption by molecules such as water and methane can produce colours that resemble those of very distant galaxies whose light has been redshifted. This similarity is the reason why brown dwarfs and high redshift galaxies can occupy overlapping regions in colour diagrams based on near-infrared filters. In the case of Kappa Tauro, the modelling indicates that a brown dwarf with a temperature near 300 kelvins can reproduce the sharp rise in brightness between the shorter and longer bands and the overall flux level in the reddest filters, while remaining below the detection limits in the bluer filters. When the observed brightness is combined with such a low temperature in the models, the implied distance places Kappa Tauro beyond 7 light-years from the Sun, significantly farther than many known very cold brown dwarfs, which tend to be discovered in the nearer solar neighbourhood. At this distance and temperature, Kappa Tauro would be both the coldest and one of the farthest such objects detected, if the brown dwarf interpretation is correct. Within the Milky Way, most known brown dwarfs have effective temperatures above this level. They are identified in surveys by their characteristic colours in near-infrared and mid-infrared bands, and by spectral features associated with cool atmospheres. As they cool below certain thresholds, their emission shifts to longer wavelengths, and they become difficult to detect in surveys that do not reach very faint flux levels in the appropriate bands. The sensitivity of the James Webb Space Telescope, especially in the reddest near-infrared filters used in the Sears field, extends the reach of such searches. It allows brown dwarf candidates that would be too faint for many previous instruments to be detected as compact points. Kappa Tauro's detection only in the 2 longest near-infrared camera bands fits this pattern. The near-infrared spectrograph data, though limited, support the idea that a smooth, cool continuum with broad molecular absorption can match the recorded spectrum. The models that treat Kappa Tauro as a brown dwarf adjust parameters such as effective temperature, surface gravity, and atmospheric composition to find combinations that reproduce the observed distribution of flux with wavelength. Among these, the most successful solutions cluster around very low temperatures. They occupy parts of parameter space that have not been widely sampled by direct observations of other brown dwarfs, but are predicted by theoretical cooling curves. In this picture, Kappa Tauro is an extraordinary example of an object already cooled to about 300 kelvins while remaining detectable at a considerable distance. Its placement in the outer regions of the Milky Way along this line of sight also has implications for how substellar objects are distributed in the galaxy. If confirmed as a brown dwarf, Kappa Tauro would trace a population of very cool low-mass bodies in the galaxy's outskirts or halo that is only beginning to be explored with sensitive infrared instruments. It would indicate that such objects are not confined to the immediate solar neighbourhood, but can exist at large distances, contributing to the overall mass budget in a way that has so far been only indirectly constrained. The brown dwarf interpretation also aligns with the idea that Kappa Tauro might be a relatively pristine object. if it formed early in the history of the Milky Way and has been cooling for a long time in a relatively undisturbed orbit, its internal composition could reflect conditions in the galaxy at the time of its formation. The study notes that if this scenario is correct, Kappa Tauro could provide a new probe of how the Milky Way assembled its mass and how low-mass objects formed in its outer regions. In this context, the interest in Kappa Tauro shifts from the very early universe to the detailed structure and history of the galaxy that surrounds the Sun. The description of Kappa Tauro as a brown dwarf candidate remains cautious. The present data allow models with very low effective temperatures and large distances to match the near-infrared camera and near-infrared spectrograph observations, and these models suggest that Kappa Tauro would be the coldest and farthest known brown dwarf if it belongs to this class. However, the same data also permit the high redshift galaxy solutions discussed earlier. The analysis therefore does not claim a definitive brown dwarf identification. It lists this scenario alongside the early galaxy interpretation as one of the two most likely options, each with its own implications, and emphasizes that additional observations are required to decide between them. Under the brown dwarf view, Kappa Tauro is a single compact object within the Milky Way, defined by its low temperature, weak infrared glow, and potential status as an extreme outlier among known substellar objects, with the current James Webb measurements providing a first but incomplete view of its properties in this framework. Inside Kappa Tauro, under the brown dwarf interpretation, conditions differ from those in a star. At its core, pressure and temperature are not high enough to sustain long-term nuclear fusion of hydrogen. Instead, the interior behaves as a dense, slowly cooling reservoir of thermal energy. When such an object forms, it contracts under gravity and heats up, but because its mass falls below the threshold for stable hydrogen, burning the core never reaches the temperatures needed to balance contraction with continuous fusion. Over time, the object cools and contracts further, until a balance is reached between gravity pulling inward and internal pressure from dense matter pushing outward. In this state, Kappa Tauro would shine mainly by releasing the heat stored from its formation and early evolution. At an effective temperature near 300 kelvins, similar to a mild room temperature in everyday terms, its surface is extremely cool compared with the surfaces of stars. The peak of its emission lies in the infrared, and very little light is radiated at visible wavelengths. The atmosphere is thick and dominated by molecules rather than atoms. Hydrogen and helium provide the bulk of the gas, but at such low temperatures heavier elements combine into molecules like water, methane, and possibly ammonia. These molecules absorb and emit radiation in broad bands, carving deep troughs and gentle peaks into the spectrum. Cloud layers may also form made of condensed compounds that appear when the local temperature and pressure allow gases to turn into liquid droplets or solid particles. These clouds scatter and absorb light, further shaping the emergent spectrum. In the models used to interpret Kappa Tauro as a brown dwarf, these atmospheric processes are essential. They explain how an object with a low effective temperature can still show strong emission in certain infrared bands, while being very faint or invisible in others. As light from deeper, hotter layers passes through the atmosphere, it encounters regions where particular molecules are abundant. At wavelengths where these molecules absorb strongly, the flux is reduced. At wavelengths where the atmosphere is more transparent, light escapes more easily, and the object appears brighter. The resulting pattern of brightness with wavelength is what the near-infrared camera and the near-infrared spectrograph detect. The internal structure beneath the atmosphere is not directly observed, but is understood from models of brown dwarf interiors. The central regions are composed of dense, partially degenerate matter, where the pressure is provided not only by thermal motions, but also by the quantum mechanical properties of electrons. This degeneracy pressure prevents further collapse even when temperatures have fallen significantly. Energy is transported from the interior to the surface by convection over much of the radius. In a convective zone, warmer material rises and cooler material sinks, mixing the interior and carrying heat outward efficiently. This convection keeps the temperature gradient steep enough to sustain a steady flow of energy from the core remnant to the surface. At the surface, radiation carries energy away into space, and over long periods the entire object cools and its luminosity decreases. The rate of cooling depends on mass and composition. More massive brown dwarfs start hotter and take longer to cool to a given temperature. Thus, an effective temperature of around 300 kelvins suggests a particular combination of mass and age. For Kappa Tauro, the models that match its observed brightness and colours as a brown dwarf imply that it has cooled for a long time, allowing its surface to reach such a low temperature while still radiating enough infrared light to be detected by the James Webb Space Telescope at more than 7 light-years away. In the outer layers, atmospheric circulation interacts with radiation. Winds driven by temperature differences and rotation may transport heat and material redistributing clouds and molecules. This can cause spatial variations in brightness on the surface. On some brown dwarfs, such variations lead to changes in observed light as the object rotates, producing small periodic fluctuations. For Kappa Tauro, the current data do not track brightness over time, so any such variability remains unknown. The measurements represent an average state integrated over the exposure times of the imaging and spectroscopic observations. The chemistry of the atmosphere is set by both local temperature and the elemental abundances inherited from the gas cloud that formed the brown dwarf. If Kappa Tauro is a pristine or nearly pristine brown dwarf in the outer Milky Way, its composition may reflect conditions in the galaxy at the time of its birth. The relative amounts of elements such as carbon, oxygen, and nitrogen influence which molecules dominate and how strong their absorption features are. These details in turn modify the shape of the spectrum that reaches the detectors. The models used in the study explore a range of compositions, but with the current limited spectrum they cannot fix the abundances precisely. They demonstrate that certain combinations of temperature and composition can reproduce the overall pattern of flux in the near-infrared camera bands and the core structure seen by the near-infrared spectrograph, without claiming a unique solution. The gravitational field at the surface of a brown dwarf is strong. Surface gravity affects atmospheric pressure profiles, and thus the depth and width of molecular absorption features. Higher gravity tends to compress the atmosphere, making line broadening more pronounced and altering the shape of the continuum. In fitting models to the data for Kappa Tauro surface gravity is one of the parameters that can be adjusted. Acceptable solutions tend to correspond to values consistent with brown, dwarf masses, rather than with planetary masses or stellar gravities, reinforcing the idea that if this scenario is correct, Kappa Tauro is a substellar object of significant mass, rather than a low-mass planet. Deeper inside, the brown dwarf's interior cools uniformly over time because convection mixes the material efficiently. Unlike stars, which can maintain stable structures for billions of years by burning fuel, brown dwarfs follow simple cooling sequences. Their luminosity and temperature steadily decline. The models that match Kappa Tauro's present state place it at a stage where its core has long since stopped any brief episodes of deuterium or lithium burning that may have occurred early in its life, leaving only residual heat as the energy source. In this long cooling phase, there is little internal evolution beyond gradual temperature decline. The object is quiet and stable with internal motions limited to convective mixing, and no violent processes like sustained fusion or large-scale flares. The radiation escaping from such an interior is nearly constant on human timescales. Over hundreds of millions or billions of years, the brown dwarf slowly grows fainter and cooler, contributing to the galaxy's population of faint infrared sources. If Capotaro occupies this regime, then the James Webb observations have caught it in a late calm phase of its thermal history. The energy it emits now is a delayed echo of the gravitational energy it released long ago during formation. From the point of view of the Milky Way, Capotaro as a brown dwarf is a small dense object following an orbit in the galaxy's outskirts. Its gravitational influence on nearby matter is minor compared with that of stars and dark matter halos. Its main observable effect is the infrared light that makes it detectable in sensitive surveys. Under this interpretation, the internal physics of Capotaro is simple in concept, but rich in detail: a core supported by degeneracy pressure, a convective envelope transporting heat, and a cool molecule-rich atmosphere, where temperature, gravity, and composition combine to imprint complex features on an otherwise smooth thermal spectrum. The current James Webb data glimpse only the outermost layers of this structure through the shape of the infrared emission. They cannot probe the interior directly, but by matching observed colours and spectra to models of brown dwarf atmospheres and cooling tracks, they allow a consistent picture of a very cold, slowly cooling substellar object to be drawn, always with the caveat that the same data can also be matched by very different models under the distant galaxy scenario. Beyond the main interpretations of Capotaro as either a very early galaxy or a very cold brown dwarf, the team considers other possible identities. These alternatives are explored not because they are expected to be common, but because the unusual combination of colours and brightness seen in the near-infrared camera and near-infrared spectrograph data invites a wide check of models. The working aim is to see whether any less standard configuration can match the observations as well as, or better than, the two leading scenarios. One group of alternatives involves galaxies that are not as extreme in redshift as the early galaxy solution, but that have unusual internal properties. For example, an odd young galaxy with a strong burst of recent star formation and particular patterns of dust and gas could, in principle, produce a spectrum where light is suppressed in some bands and enhanced in others. Intense emission lines from ionized gas, when shifted by cosmic expansion, might land within certain filters and boost the measured flux, while absorption features could weaken the light in adjacent bands. By adjusting the balance between stellar continuum emission lines, dust and gas, such models can sometimes reproduce large changes in brightness between filters without placing the source at the highest redshifts. The team therefore includes models of young galaxies with distinctive emission line strengths and dust properties in their comparisons. When these models are passed through the same filter responses and sampled at the spectrograph wavelengths, some do show sharp rises in flux across the near-infrared range. However, matching the precise shape seen for Capotaro is difficult. Many of these odd galaxy models that stay at more moderate redshifts predict too much light in the shorter wavelength bands where Capotaro is not detected, or they produce strong spectral features in regions where the available near-infrared spectrograph data do not show significant structure above the noise. The best-fitting versions still do not clearly surpass the high redshift galaxy models in consistency with the data. Another group of alternatives treats Capotaro as a planetary mass object, perhaps a free-floating exoplanet not bound to a nearby star. Such an object would be smaller and less massive than a brown dwarf, but could have a similar atmospheric structure if its temperature and composition are comparable. Models of cool exoplanet atmospheres with molecules such as water, methane, and other species can generate infrared spectra with deep absorption bands and peaks that might mimic the observed colours. In this scenario, Capotaro would be a very cold planet-sized body, within the Milky Way radiating weak thermal light, and detected only because the James Webb Space Telescope is sensitive enough in the reddest near-infrared bands. When these planetary models are fitted to the data, some can reproduce aspects of the near-infrared camera photometry, especially the relative faintness at shorter wavelengths, and the stronger flux in the longest bands. However, they also tend to imply surface gravities and sizes that differ from those preferred by the best fits, and they often require distances or luminosities that are not well supported by current understanding of how common such free-floating planets at very low temperatures and large distances should be. In addition, there is significant overlap between the atmospheric features of the coolest brown dwarfs and those of massive young planets, making it difficult to justify a separate planetary interpretation when brown dwarf models already occupy the same region of parameter space with fewer additional assumptions. The team also considers the possibility of blended or composite sources where more than one object contributes to the observed light. For instance, a distant galaxy and a closer cool star or brown dwarf could in principle lie along nearly the same line of sight. Their combined emission would appear as a single point in the images. If one source dominated in some filters and the other in different filters, the resulting colours could be unusual. To test this, models that some light from two components at different distances and with different spectra are examined. These composite models can produce a wide variety of shapes in the spectral energy distribution. However, they introduce many additional free parameters such as the brightness and spectra of each component and their relative alignment, while the present data provide only limited constraints. In most cases, the composite explanations do not improve the fit in a clear or robust way compared with the single object models. Without independent evidence for a blend such as a resolved structure or characteristic spectral signatures, the team regards these multi-component scenarios as possible but not strongly supported. There's also the question of whether Kappa Tauro might be a member of a rare class of transient or variable sources caught in a particular phase. Certain explosive or eruptive events can produce brief changes in brightness and spectral shape. However, the SEERS imaging and the ENIA-SPEC observations are separated in time, and there is no clear evidence in the current data for strong variability. The object appears with consistent properties in the available exposures within measurement uncertainties. Moreover, the spectrum does not show the sharp features often associated with transient events, such as strong emission lines or unusual continua. Given these considerations, the transient explanation is not favoured by the present observations. Across all these alternative checks, a pattern emerges. Many exotic models are capable of reproducing some parts of the data for Kappa Tauro, especially when parameters are tuned. An odd young galaxy at moderate redshift can be made to match some colours. Peculiar exoplanet model can mimic certain aspects of the spectrum, and composite or transient scenarios can be constructed that pass through key points in the photometry. Yet when the entire data set is considered together, including non-detections, detections, and the limited spectral shape, none of these alternatives provides a clearly superior fit. They often require fine-tuned conditions, produce mismatches in parts of the spectrum, or rely on populations of objects whose expected numbers are uncertain. The authors of the study therefore treat these exotic scenarios as part of the exploratory phase, rather than as leading candidates. They note that while a range of configurations can be constructed to resemble Kappa Tauro in model space, the current data do not demand complicated explanations. Instead, they point to two broad, relatively simple classes that remain consistently compatible with both the near-infrared camera and near-infrared spectrograph measurements, a very early massive galaxy at high redshift and a very cold brown dwarf in the outer Milky Way. The other options are not ruled out in an absolute sense, but they are not preferred when the quality and completeness of the match to the data are weighed against the complexity of the models. In this way, the exploration of exotic paths clarifies the situation by showing that many unusual possibilities do not provide decisive improvements, and that the main uncertainty lies in distinguishing between two physically different but comparably successful interpretations supported by the present James Webb observations. After fitting many models and checking a wide range of possibilities, the study reaches a point where the limits of the current data determine how far the interpretation of Kappa Tauro can go. The near-infrared camera imaging and the near-infrared spectrograph observations together provide a clearer picture than the early coarser data did, yet they still leave key questions unresolved. The measurements show that Kappa Tauro is a compact source, bright in the two longest near-infrared bands and undetected in the shorter ones, with a faint spectrum that confirms the general level of flux in the reddest wavelengths. They show that its colours place it in a region of parameter space where very distant galaxies and very cool substellar objects overlap. They show that simple ordinary models of moderate redshift galaxies and typical brown dwarfs fail to match its properties. Beyond these statements, the data become less decisive. One of the primary limitations lies in the depth and resolution of the spectrum. The near-infrared spectrograph observation is sufficient to trace a broad continuum, but not to reveal clear, narrow features that could pin down a precise redshift or unambiguous atmospheric signatures. Strong emission or absorption lines that might distinguish between a high redshift galaxy and an extremely cold brown dwarf either fall below the detection threshold or lie outside the wavelength range covered in this observation. As a result, the spectrum can be matched by more than one class of models, and the statistical differences between these fits are not large enough to single out a unique solution. The imaging data also carry inherent constraints. In the bands where Kappa Tauro is not detected, the measurements provide only upper limits on the flux. These limits are important because they restrict models that would otherwise predict significant brightness at those wavelengths, but they still allow a range of faint non-zero values. In the reddest bands, the detections are strong enough to define reliable fluxes, yet the uncertainties remain significant. When models are compared with these data, different combinations of physical parameters can produce fits that lie within the observational error bars. The formal best fit may favour one scenario slightly, but the differences in quality of fit are not sufficient to rule out the other leading scenario. Under these conditions, the study cannot claim that Kappa Tauro is definitively a very early galaxy or definitively a very cold brown dwarf. It can only state that both possibilities remain viable. Another limitation comes from the fact that the object is unresolved in the images. The James Webb Space Telescope sees Kappa Tauro as a point source with no measurable extension beyond the point spread function of the instrument. This is consistent with both a small distant galaxy and a compact object within the Milky Way. Without spatially resolved structure, there is no direct way to estimate a physical size. The models must treat size as an inferred quantity that follows from the assumed distance and luminosity. This increases the dependence on theoretical expectations rather than purely observational constraints. The lack of time series data adds a further degree of uncertainty. If Kappa Tauro were monitored over time, variability studies might reveal rotational modulations typical of brown dwarf atmospheres or transient events associated with certain types of galaxies. The available Sears imaging and the near-spec observation, however, provide only snapshots separated by limited intervals. Within those snapshots, Kappa Tauro appears stable within the errors, but this stability over a short baseline does not strongly favour one interpretation over the other. From an observational standpoint, the study is based on a preprint that has not yet undergone formal peer review at the time it is written. The analysis is careful and methodical, but the authors themselves present their conclusions as provisional. They emphasise that the current data are not enough to decide between the main scenarios and that additional, more precise measurements of Kappa Tauro's light are needed. They avoid strong claims about having found the oldest known galaxy or the coldest known brown dwarf. Instead, they frame Kappa Tauro as one of the most puzzling discoveries from the James Webb Space Telescope to date, an object that pushes against the edges of current models in whichever category it is placed. The question of whether Kappa Tauro is the oldest galaxy in the universe remains openly conditional. Under the early galaxy interpretation, the best-fitting models place its formation around 100 million years after the Big Bang, which would make it older, in the sense of appearing earlier in cosmic time than previously known galaxy candidates, by roughly 200 million years. However, this claim depends on accepting the high redshift solution and the associated conversion from observed flux to intrinsic properties, since the same data can be matched by the brown dwarf scenario, and since the spectrum does not provide an unambiguous redshift, the study does not adopt the label of confirmed oldest galaxy. It treats this status as a possibility that is intriguing but not established. Similarly, in the brown dwarf interpretation, Kappa would be the coldest and farthest known example of its kind, with an effective temperature around 300 kelvins and a distance of more than 7 light-years. Yet this conclusion also rests on model fits to limited data. If further observations were to show that Kappa Tauro lies at a different temperature or distance, or if its nature as a substellar object were ruled out, this status would change. The authors therefore describe it as a candidate for an extreme brown dwarf, not as a confirmed member of a new category. The inconclusive nature of the results is not a failure of the observations, but an honest reflection of their current scope. The James Webb Space Telescope has revealed Kappa Tauro and provided a first set of detailed measurements that were not possible before. These data are sufficient to show that the object is unusual and to narrow down the range of plausible explanations, but they are not yet sufficient to deliver a single definitive answer. The remaining uncertainty is explained clearly in the study. It stems from the signal to noise of the spectrum, the reliance on upper limits in several bands, the degeneracies between high redshift galaxy and very cool brown dwarf models in near-infrared colours, and the lack of independent constraints such as parallax for distance or additional spectral coverage. In this sense, the present work is a step in an ongoing process. It defines what is known about Kappa Tauro at this stage, its photometric behaviour, its spectral outline, the sets of models that can fit the data, and the physical implications of each main scenario. It also defines what is not known, its true distance, its exact temperature and composition, its detailed internal structure, and its precise place in either the early universe or the Milky Way. The study ends this phase by stating that Kappa Tauro remains a source with 2 leading identities, and no final verdict illustrating how new observations can open questions as well as answer them, and how at the current limits of sensitivity and modelling, multiple interpretations can share the same faint red infrared signal. As the analysis of Kappa Tauro reaches its present limits, attention turns toward what further observations can do. The existing near-infrared camera and near-infrared spectrograph data have defined the object as a compact, unusually coloured source that fits either a very early galaxy model or a very cold brown dwarf model, with other options less favoured. To move beyond this shared space of solutions, astronomers plan measurements that can separate the signatures of high redshift galaxies from those of cool substellar bodies more clearly. Central to these plans is the idea of obtaining deeper and more finely sampled spectra. A longer exposure with the near-infrared spectrograph, possibly using different dispersing elements or configurations, could improve the signal-to-noise across the wavelengths, where Kappa Tauro is bright. With more sensitive spectra, faint emission or absorption features might emerge from the noise. For a distant galaxy, these could include lines from ionized gas such as those produced by hydrogen, and oxygen shifted to specific near-infrared wavelengths by cosmic expansion. Their presence and positions would provide a direct measure of redshift. For a brown dwarf, deeper spectra might reveal more clearly the broad molecular bands of water and methane, as well as the detailed shape of the continuum that depends on temperature and surface gravity. Even weak features, if measured reliably, could break the degeneracy that now allows both scenarios. Additional imaging can also help. Observations in more filters extending both to slightly shorter and longer wavelengths would fill gaps in the current coverage and refine the shape of the spectral energy distribution. Mid-infrared measurements, which probe even longer wavelengths than the present near-infrared camera bands, are particularly valuable. A very high redshift galaxy and a very cold brown dwarf differ in how their brightness declines or rises into the mid-infrared. By comparing fluxes across a broader range of wavelengths, astronomers can test whether Capitaro follows the pattern expected for a compact galaxy dominated by starlight or the smoother thermal spectrum of a cooling substellar object. Repeated imaging over time can search for variability. Brown dwarfs often show small changes in brightness as they rotate, bringing different atmospheric regions into view. A distant galaxy, in contrast, is less likely to vary on short timescales at the modest levels accessible in these data. A series of observations spaced over months or years could therefore reveal low-amplitude, periodic or irregular variations that would support the brown dwarf interpretation, or a stable light curve that would be more in line with a steady galaxy. Such time series measurements require careful planning and long-term access to the same field, but they are within the capabilities of the observatory. Beyond direct observations of Capitaro, astronomers look for similar objects in other deep fields. The methods used to discover Capitaro in the Cosmic Evolution Early Release Science Survey can be applied to additional James Webb programs. By searching for points of light that are absent in several near-infrared bands and present only in the longest ones, with matching unusual colors, they can build a sample of sources that occupy the same ambiguous region of parameter space. If many such objects are found, and most turn out after further study to be brown dwarfs, then the balance of probabilities for Capitaro would tilt toward the substellar explanation. If instead a significant fraction are confirmed as very distant galaxies by precise redshift measurements, then the early galaxy scenario for Capitaro would gain support. In either case, Capitaro becomes part of a broader effort to map the populations that lie at the boundaries of current models. The process of securing these new data is deliberate. Proposals for telescope time must be written, reviewed and scheduled within the overall program of the observatory, which serves many scientific goals. The study of Capitaro notes that the team has requested additional James Webb observations to gather more precise light from this object. If approved and carried out, these observations will gradually add to the set of measurements, perhaps reducing uncertainties and closing off some of the parameter space that now remains open. Until then, the present data stand as the best available description. Over longer timescales, even more tools may come into play. Future observatories with higher sensitivity, different wavelength coverage, or improved angular resolution could contribute complementary information. Ground-based telescopes equipped with advanced instruments might attempt to measure subtle motions such as parallax that would indicate whether Capitaro shares the motion of nearby stars or remains fixed at a cosmological distance. Radio or sub-millimeter facilities could search for emission associated with cold gas or dust if the object is a galaxy. Each additional piece of information would refine the picture, though none is available yet. In this stage, the story of Capitaro is one of careful waiting as well as active planning. The James Webb Space Telescope has opened a window in which such faint and unusual sources can be detected and characterized to a first level. Follow-up observations will deepen that characterization. For now, astronomers know that Capitaro sits at a point where models of the very early universe and models of very cool substellar objects meet. The next steps aim to distinguish which of these frameworks truly describes the source. Until further data arrive, the object remains in a suspended state between identities defined by the light already recorded and by the plans laid out to observe it again under the steady, patient operation of the observatory in deep space.